Hi, welcome to lecture 2.8 of the SAGE-based course on Monte Carlo methods. We were just looking at the axiomatic definition of probability and what it means, some motivation, lots of examples, and some properties that follow from these definitions. Now let's look at example 5. It's about experiments, outcomes, sample space, events, and the probability of events. Just covering again all these new terms you've learned in the last couple videos. So let's go back to the well-mixed fruit bowl example. So the fruit bowl contained 2 oranges, 3 apples, and 1 lemon. And the experiment is to take one piece of fruit from the bowl, and the outcome is the type of fruit we get. So here the sample space, capital Omega, was orange, apple, and lemon. Now let's use SAGE and the list in SAGE in particular to create the sample space. Okay, so we can say the variable called sample space equals or is assigned the list orange, apple, and lemon. So now in SAGE memory we have sample space. So if I ask what is sample space, I get orange, apple, and lemon as a list. We can also use a list to specify what the probability of each outcome in the sample space is. The probabilities can be calculated by knowing how many fruits of each kind are there in the bowl. We say that the fruit bowl is well stirred, which essentially means that when we pick a fruit, it really is a random sample from the bowl. For example, we have not carefully put all the apples on the top so that someone will almost certainly get an apple when they take a fruit. More on this later in the course, alright? So note that the probabilities encoded by a list named probabilities are in the same order as the outcomes in the sample space. So here is probabilities, the variable, and it's being assigned the list of the actual probabilities of the 2/6 is the probability of orange, 3/6 is the probability of drawing an apple because there are 3 apples, and 1/6 is the probability of drawing a lemon from this well-stirred bowl because only 1 lemon out of the 6 fruits. If I evaluate this, I get the list once again. So let's make sure BROBABILITIES. What is that? Well, that's been assigned the list 1/3, 1/2, and 1/6. Note that SAGE has simplified 2/6, the rational number 2/6, to 1/3, which is the same. That's okay. Prob map fruit bowl. Here's our next thing we're going to assign, next variable. Prob map fruit bowl is a variable that's being assigned this thing called probi map. Okay, so probi map is a probability map. It's a class in SAGE. You don't have to know all the details. They're actually in the bottom of this worksheet, and if you want to look at the code, you can look at it, especially if you're bored. But for now, just think of it as a built-in method for this course. And what does probi map do? It's going to take 2 arguments. The first argument is called S space. S space equals sample space. So we have to tell what the sample space is for the probi map. And the second argument is probs, and probs is assigned probabilities. So remember, probabilities is the list we just made up here, and sample space again is the list we actually just assigned here. Right? So now we pass in these 2 arguments to probi map, and what it will do for you is make a probability map for us. Now once we have done this assignment, prob map fruit bowl, then we can ask SAGE to display prob map fruit bowl. And then it gives us back, if you recognize, a dictionary. Orange is 0.33, the lemon is an outcome from the sample space, and its probability is 0.167, that's 1/6, and apple is another outcome, and its probability is 0.5, which is this 1/2. So we have probabilities associated with events. That sounds like a good use for a dictionary. That's basically what we just did, and we wrapped up the dictionary in some extra code that does things like check that the probabilities add to 1 and that each element in the list of outcomes we have given is unique. If you're interested in programming, we have called our own type or class called ProbiMap. So you can look at it below if you want, but don't worry about it for this course. Once this class has been coded, we create a ProbiMap by providing the sample space and the probabilities. You don't have to worry about how the class is implemented, but note that in computational statistics, you may often want to use the computer to create a computerized representation of a concept. That's what a class really does. Okay, it just has some way of implementing a particular concept. Once the concept, in this case a discrete probability map, has been defined into a class, then we can use the computer to automate the mundane tasks of large-scale computations. So in this case, we can have a very large finite sample space, and our ProbiMap class will actually do the dirty work for you and do a lot of the error checking under the hood. So we can use our probability map to find the probabilities of single outcomes like this. So if I ask, what is the probmap fruit bowl dot p for the probability of the outcome lemon, I pass in an argument like this, and it should give me the probability of drawing a lemon from probmap fruit bowl. We can also use our probability map to find the probability of an event or set of outcomes, right? So we can simply add now the list of the outcomes that make up the event, lemon, orange. And it'll simply add the probability of the lemon to the probability of the orange, and we get half, right? Because half comes from adding the lemon probability to the orange probability, so that's 0.33 plus 0.167, which is just half. Basically, the probability map is essentially a dictionary under the hood. Next, we will obtain the set of all events, right? The largest sigma algebra or sigma field in the math lingo from the outcomes in our sample space via the subset function, and find the probability of each event using our ProbiMap in a for loop. Okay, so this is not something you should know in too much detail. I just want you to understand it as a user here. So what we've done is simply gone through all possible subsets. So that's what this is. The function subsets of sample space simply generates all the subsets. So here is the empty set. So nothing happened, or the orange, lemon, apple by itself, the outcomes, or these events, orange, lemon, or orange, apple, lemon, apple, or all of them, which is the sample space, orange, lemon, and apple. So it simply goes through them and lists it out. Now we have not done loops yet. That's why I don't want you to get too caught up in this right now, but just as a foretaste, here we use a for loop to print out the computed probabilities for each event in the set of all events. Okay, so we simply go through all the events and find out what its probabilities are. It was a good time to pause the video. There was quite a lot in this lecture. Please go back and go through these things slowly and finally work out through these U-tries, and you should be good to go. And here's how you can see how the class for probability map was created if you're a computer science student especially. Okay, but you're not expected to understand how to implement this in this course. Bye.